Welcome to a lesson with Dr. Powell. Let's look at how we can use the idea that the cumulative area function of the area between the curve of f prime and the x-axis is actually an antiderivative of f prime, meaning specifically that it's a shift of the specific antiderivative of f that we're after, so that the change of area is in the outputs of this area function is actually exactly equal to the change of the function f that we're looking for on a specific interval. We're going to use this idea in an example. We're going to start with this graph right here, and we're going to use it to draw the graph of the specific antiderivative that we're after, using maybe a point on this graph. So let's suppose that we know that the antiderivative of f prime that we're after goes to the point 0, 1. What happens next? So what happens next is we can see this right here. Notice that in this graph of the derivative, I've actually written out areas. This is a half circle of radius 2. Using pi times radius squared and dividing by 2, we get that this area is 2 pi. Likewise, this is a quarter circle of area pi fourths. This is a triangle of area 1. This is a triangle of area 3 halves. Using these ideas, we're going to mark out where the local min and max are of the actual function f, and also where the inflections occur. First, where do min and maxes occur? So a maximum occurs where the graph itself changes from increasing to decreasing. And we can see that in the graph of the derivative. Where the derivative is positive, the function is increasing. Where it's negative, the function is decreasing. So positive derivative, so increasing, negative derivative, decreasing. Right there, there's a max. So if we can find the y value at this point, that would be great. So what we do is we know we start here, and then we're going to add 2 pi, because the outputs of the graph of f actually go up by 2 pi, just like the area goes up by 2 pi right here. So we know that the specific y value has increased from 1 to 1 plus 2 pi exactly right here. So just by looking at this graph and knowing the areas between things, we can actually know the specific y values on this graph. So we know what the specific maximum is right here. Now, what about minimum? Let's just see what happens with the minimum. Well, right here we would, because the derivative is negative, so decreasing, then it changes to positive. So the function will be increasing, so we'll naturally get a minimum here at this point. So this is 4, 5, 6, 7. This is at the x value of 7. So this one right here. Now let's see what's happened. Well, we were at 1 plus 2 pi, and we've gone down. How much have we gone down by? Since this is a negative area, we're going down by it. The y values are changing. Well, we drop pi fourths, and then we drop 1. So since we drop 1, this 1 goes away. So we're left with 2 pi minus pi fourths, which ends up being 7 pi fourths. So we end up getting this local minimum. Great. So we've actually notated where the local min and max are. Now, how can we figure out? Now, notice in this graph, I've put in the inflection points. How do I know where inflection points are? Now, inflection points occur precisely where the second derivative changes from positive to negative. But you can actually see that in the graph of the derivative itself. Notice how the derivative, when the derivative is increasing, that means its derivative, which is f double prime, ends up being positive. So instead of actually knowing what this graph is, let's just look at where f prime is going up. So it's going up, and then when it changes to going down, hey, that's like a maximum here. In fact, you can find inflection points over here by finding minimums and maximums, or mins and maxes up here in the derivative itself. So notice how we have a maximum of the derivative here. That's going to be an inflection point. And we know we get it we know what the y value is, because from the area from here to here is actually 1/2 of 2 pi, it's pi. So we're going up pi. Notice I've notated that. So right here at 2, I have the inflection, and it's a 1 plus pi. Notice how I graph this. It's concave up and concave down. Concave up because this derivative is increasing. So when the derivative is increasing, we have concave up because the second derivative is positive. Then right here, first derivative is decreasing, which means we have concave down to here. Okay, next we have an inflection over here because it's a minimum. So that occurs at right here at x value of 5. And what's been done is we've dropped our y values of the function f right here, have dropped by pi fourths from the peak. 1 plus 2 pi minus pi fourths takes us to 1 plus 7 pi fourths. So I know the exact coordinate of that point right there. Now, not to mention, we need to include endpoints when we're thinking about local mins and maxes, because those potentially could give us something there. So here we'll put in, let's figure out what the endpoint is right here. Well, if we just go from this minimum here, notice what we're just adding three halves on. Notice that's how we get this y value here, since we're just adding the area amount as the change amount here of the function. And so we get a nice little graph of f. Thanks for watching.